Okay, let's dive right into this explainer. Today, we're looking at the 2026 MATE ROV competition. It's this incredible, high-stakes arena where student-built robots face off against some of the absolute most extreme real-world global challenges on Earth. The entire theme this year? It's all about pushing performance, science, technology, and discovery in incredibly harsh environments.
So the crucial point we are starting with is a massive, high-stakes question. How do we operate in, and ultimately protect, an ocean we can barely even reach? We've got this amazing global community of learners and innovators, right? Well, this year, the client issuing the request for proposals is us. We're challenging teams to build real, working solutions for the absolute hardest-to-access environments on the planet.
Let's move to the macro level and look at Part 1, the Global Ocean Challenge.
Now, what's really interesting here is the sheer scale of what we call the cryosphere. This challenge aligns directly with the UN Decade of Action to protect Earth's frozen regions. We're talking this vast, freezing expanse of polar ice sheets, sea ice, mountain glaciers, and permafrost. It actually covers about 10% of the Earth's landmass and, believe it or not, dictates our entire global climate. It might seem super remote, but changes here literally impact billions of people worldwide.
And this brilliantly illustrates the stakes. Roughly 70% of the world's fresh water is locked up right here in the ice and snow of the cryosphere. Think about that for a second. That means most of our river water and our drinking water ultimately comes from this exact snow and ice melt. It makes protecting these frozen regions absolutely vital to our everyday survival.
All right, let's move on to Part 2, Extreme Testing in St. John's. To build technologies that can actually survive these extreme conditions, well, you have to test them in extremes, which brings us to the host city for the 2026 World Championship, St. John's, Newfoundland and Labrador. It's home to some of the most advanced ocean testing facilities on the planet. Teams are going to push their robots to the absolute limit in places like the Marine Institute's Flume Tank. This thing is the world's largest, holding 1.7 million liters of water where they can generate massive, high-velocity currents. They'll even use an ice tank that simulates Arctic conditions down to a bone-chilling negative 25 degrees Celsius. Basically, if your tech works here, it'll work anywhere.
Okay, jumping right into Part 3, Real-World ROV Missions.
Let's dive into the core of the competition. Teams have just 15 minutes to execute 4 rapid-fire, high-stakes tasks flawlessly. Task 1 takes us to the Funk Island Deep Marine Refuge. Here, teams have to navigate really strong currents to collect species and document a highly dense, recently discovered cold-water coral garden. What's absolutely wild here is that these soft corals were found at unusually shallow depths of less than 200 meters, and they're so densely packed together that researchers can't even see the seafloor beneath them.
So how do you map a fragile ecosystem like that without destroying it? You rely on photogrammetry. Your ROV needs to fly a super precise path in a simulated current to stitch a bunch of two-dimensional images together into a perfect 3D model. It's like a giant puzzle, providing a highly efficient, completely non-invasive way for scientists to monitor this incredible habitat over time.
Moving on to Task 2, what's really interesting here is the literal collision of extremes. Teams have to survey an iceberg's keel depth to calculate its threat level to offshore oil platforms like Hibernia. Because roughly 90% of an iceberg's mass is completely hidden underwater, getting accurate keel depth and heading data is absolutely critical for avoiding a catastrophic collision.
Also in Task 2, robots are tackling a major conservation challenge. With fewer than 400 North Atlantic right whales left, traditional fishing gear poses a massive entanglement risk. So teams will simulate releasing a buoy on modern, whale-safe ropeless fishing gear using an acoustic signal, and then recover a lobster pot. It's directly applying engineering to protect an endangered species. Alongside this, teams will also be replacing eDNA sensors to help scientists catalog invasive species, like the European green crab.
Let's scale things up for Task 3 and see how this builds into global energy solutions. Meeting the world's energy needs requires a really balanced portfolio, right? Like marrying renewable offshore wind power directly to offshore oil rigs. We are looking at massive infrastructure operating dynamically right out in the open ocean. Modeled after Equinor's Hywind Tampen in the North Sea, teams are stepping into the role of subsea technicians. They're going to install a power connector to link a hybrid energy grid. But drilling the anchors for these massive turbines is incredibly noisy. So teams must also deploy a bubble curtain around the site. This acts to absorb the sound energy, effectively protecting local marine life from all that deafening construction noise. Pretty clever, right?
Which brings us to Part 4, operating under the ice.
Now, at the World Championship, this task literally takes place in a refrigerated ice tank. Inspired by the massive GO BGC project, which is trying to deploy 500 robotic profiling floats to track global ocean health, teams have to independently design and construct a vertical profiling float. And here's the catch. Surfacing under a solid ice sheet would instantly crush the float's delicate sensors and antennas. So teams must engineer really sophisticated ice avoidance capabilities into their designs.
And this brilliantly illustrates the required behavior. It's a completely autonomous task requiring absolute precision. Your float must communicate with the mission station, descend, hold perfectly at a depth of 2.5 meters, and then hold again at 40 centimeters, completely under the ice. It has to complete 2 vertical profiles and, crucially, only transmit its stored data once it is safely recovered from the freezing depths.
Okay, let's pivot to Part 5. Build your startup company.
Remember, you aren't just building a robot here. You are pitching a full-fledged startup company to real-world clients. You need a CEO, a CFO, an R&D team, the whole shebang. Out of the 745 total points available, your underwater product demos definitely hold the most weight at 375 points. But make no mistake, you are heavily graded on your technical documentation, your engineering presentations, your marketing displays, and your rigorous adherence to safety protocols. Every detail matters.
Now, what's really interesting here is the strict engineering trade-off regarding your vehicle's physical footprint. Because you're operating in remote, harsh environments, deployment logistics truly matter. Build a highly capable system under 15 kilograms, and your company earns a sweet 10-point bonus. But cross that 25-kilogram threshold, your vehicle is completely disqualified from the product demonstration. Boom. It forces incredible discipline in your system design.
Ultimately, this whole competition is about forging the exact entrepreneurial, technical, and critical thinking skills demanded by the future STEM workforce. From project management and machine learning to high-stakes collaboration and overcoming literal extreme physical obstacles, you are building the exact toolkit required to solve the complex problems of tomorrow.
So as you prepare to engineer solutions for our planet's most extreme, frozen environments, the question isn't just whether you can build a cool robot. The real question is, are you ready to launch a startup that could actually help save our oceans?